Okay, so we are almost at the end of this chapter on link prediction, and today we will discuss a beautiful algorithm called supervised random walk. And supervised random walk algorithm, although it was proposed in 2011, but this is by far one of the method that people use extensively for link prediction. And the beauty about this method, the unique point about this method is that it actually captures the topological structure of a network as well as the meta information of nodes and edges. Okay, so far the methods that we have discussed, we have observed that mostly we look at the topological structure, right? We look at whether they are connected in 2 hops, 3 hops, whether they have common neighbors and how these neighbors are distributed. We look at we basically try to understand, try to unfold the underlying hierarchical structure of a network and so on. But this was, to the best of my knowledge, this was the first algorithm which combined the idea of random walk based methods for link prediction and how one can use the meta information, node level information, edge level information, right, into the random walk process for link prediction. Okay. So and this method was proposed by Uriel Escobic and his team in 2011-2012, right, during that time. So what is random walk? We all know what is random walk. Basically, a random walker starts from a particular node, and the worker essentially chooses one of the outgoing nodes uniformly at random, and then follows that edge and then basically moves to the next node, right? So by default random walk is random because we are not making it biased, but in this particular algorithm they suggested that how we can make the algorithm, how can we make the random walk process biased. Okay, and what do you mean by bias? So I actually when this random walk process will go on, we would essentially insist the random walker to move through those paths, right, which we want them to move, right? So we already fix a preference and we allow the random walker to basically follow, most of the times follow those paths. Okay, so a random walk based method which essentially combines node level as well as edge level attributes along with the network topology. This is the unique selling point of supervised random walk, and then it basically predicts and ranks all possible links which are going to form. Okay, so the use of positive and negative samples to assign a score, right, or edge strength to each edge. So what it would do, we will discuss. It would over time it would assign a strength of an edge or strength of a node pair. Okay. Now the strength of an edge, I mean one may say that okay, the strength of an edge can easily be obtained from the weight, right, the weight of an edge, right, but most of the networks are unweighted, right. So we will see how we can use node attributes and edge attributes to measure the strength of a node pair. The node pair can have an edge, right, in between them, or a node pair may not have edge, but we can predict the strength of these two nodes. Okay, so, and remember the score that we are going to compute, this edge strength, this is a parametric, this is a parametric function. Okay, this is parameterized by W, I mean a set of parameters which we will discuss. Therefore, and these parameters will be learned over time. Okay, so if this is not clear at this moment, just hold on, we will discuss elaborately in the subsequent slides. So the score, this edge strength score, this basically dictates the random walker to visit certain edges more often than the others. Okay, therefore I mentioned that this is basically a biased random walk. We bias the random walk process so that the walker essentially moves through those edges which have high edge strength. Okay, and then we use some sort of supervised learning paradigm to learn these weights, and we will see that how eventually we would be able to and when we learn this weight, right, naturally we can measure the strength of a node pair. Now if we measure the strength of a node pair, we can easily identify those node pairs which have high strength, and essentially you can say that look, possibly these two node pairs, these types of node pairs with a high strength, they would form edges in the near future. Okay, so it is biased random walk so that it visits positive samples more often than the negative samples. What do you mean by positive samples? So positive samples are those nodes which are already connected to a given node. Say for example, you are standing on a particular node and you know that this node U is connected to W, V, X, right, but it is not connected to A, B, C, for example. So for the random walk, so U, W, X, V, W, X, these nodes are basically positive nodes and other nodes are negative nodes. Okay, so we bias the random walk to move to basically walk to the move to the positive nodes more often than the negative nodes, and then we essentially over this over the iterations we essentially follow the PageRank kind of process, and we will see that we get a stationary distribution, and that stationary distribution will basically help you identify nodes which are highly likely to be connected. Okay. So let's look at the formal definition of supervised random walk. So you are given a graph G, V, comma E, and you are also given a set of nodes, set of positive nodes. Now this set of positive nodes are those which are connected. Okay, you can also say that the set of positive nodes are those which you prefer to visit. Okay, so D is a set of positive nodes denoted by D1, D2, dot dot Dm, and L is the set of negative nodes which are not connected. Of course, this set would be much higher than the positive node, but that is okay, right? And we basically learn this kind of function. This is basically a function called psi. Now psi xy, psi sub xy is a combination of node level and edge level attributes for a node pair x and y. Okay, say for example x and y, they are two users. Okay, so x has say attributes like age, gender, job, location. Y also has the same attributes. So since let's say x and y are not connected, right, so we can come up with the function psi which takes into account the attributes of x and y and produces a value, a real value, and this real value is indicates the strength of the pair of nodes. Okay, and we will see that the output of this, okay, will then be passed through a function f which is parameterized by w or omega whatever, right. So this w will be learned over time. Okay, so then based on that we compute the edge strength. So we basically have three things here. The first one is this function psi which combines the node features, I mean the features of two nodes, right, and produces something, produces a number for example or a vector, right, and then that is passed through this function f. Okay, let's say the attributes the attributes of x is 2, 1, 0, 2 and attributes of y is 1, 0, 1, 1, right. Now, the psi function can simply be the dot product, let us say, right. Dot product will basically produce a scalar number. So, this dot product value will be passed through this function f. Now, f is a parametric function, right. Say let's say it is not a dot product, it is just a element wise multiplication. So, 2 times 1 2, 1 times 0 0, 0 times 1 0 and 2 times 1 2. Okay. So, the output of this psi function is essentially a vector 2 0 0 2, right. And say you have this attribute, you have this function f which has 4 parameters w1, w2, w3, w4, and essentially let us say the simple way to combine this thing is f w is w1 x1 plus w2 x2 plus w3 x3 plus w4 x4. So, in our case this would be w1 2 plus w2 0 plus w3 0 plus w4 2. So, it will produce a scalar number, right, and this is your AUV, right. So, AUV is essentially kind of a edge strength, you would say, edge strength or whatever, a pair strength of a pair of nodes, okay. Then what we do, we compute a transition matrix. Now, remember, whenever we do random walk process, we need some transition matrix. The transition matrix can be the adjacency matrix itself or it can be computed in different ways. So, in our case it basically is computed in a different manner, okay. So, this Q dash is what? Q dash is AUV divided by sum of AUW for all W such as U and W are connected, belongs to this edge set E, right. So, what does it mean? It means that, say this is U, okay, these are different W's, you got AUV, AUW and so on and so forth. Now, you basically normalize it so that it becomes a stochastic matrix, right. The sum should be 1 so that when we do this page rank process, right, you get a transition matrix and it converges, okay. So, this Q matrix, Q dash, right, Q dash is a matrix, right, n cross n matrix, and this is the stochastic transition matrix. Remember, Q and A is adjacency matrix, they are different, right, because here Q is exhaustive in the sense that you are measuring this Q dash UV, right, for all pairs of nodes, whereas A, what I mean to say is that if you look at Q dash, you will see cells, most of the cells are non-zero, whereas in case of A is a adjacency matrix and its parts, therefore most of the cells will be 0. Okay. Now, what you do, so from the stochastic matrix, from the stochastic transition matrix, you get the actual transition matrix, right, and remember what we do here, we use something called random walk with restart, and we have already discussed what is random walk with restart in the chapter on link analysis, right. So, the idea behind random walk with restart is that you start from a node U, right, and you follow one of its outgoing edges, right, uniformly at random, move there, right. Now, from this node you either choose one of the outgoing edges or you jump to the original node again. So with certain probability you choose one of the outgoing edges, and with the remaining 1 minus that probability you then jump to the previous node, seed node. Right. So this is random walk with restart. So you see, in random walk with restart there are two components. The first component is the one that we already derived, which is Q dash. It's a stochastic matrix, and using stochastic matrix you do the random walk process. Remember, in the normal random walk with restart we use adjacency matrix for this, all this deciding whether to jump or not, or which edge to follow. But here the random walk process is happening on this Q dash adjacency matrix, or Q dash whatever transition matrix, right. So you basically have all pairs of nodes, and all pairs of nodes are virtually connected with some edge strengths, and you decide based on the edge strength value. Okay. So in other words, we are computing the entire thing, the entire process on a modified graph, right. This modified graph is basically generated based on this Q dash, okay, where nodes are connected, nodes are virtually connected, and the connection strength is derived by the edge strength that we discussed. Okay. So this part is the random jump part. But this part is the part based on which you basically choose one of the outgoing edges, and this is alpha. So alpha 1 minus alpha, this damping factor, right, in case of PageRank we discussed. Okay. And this is alpha times 1. It means that you are only allowed to move to the source node, jump to the source node. Okay. So this is now the adjacency matrix, or whatever transition matrix, final transition matrix. Okay. Now if you only consider this part, then this is a pure random walk on the adjacency, on the modified transition matrix. But since you add this part also, it's a random walk with restart. Okay. And what is the expectation? So when we start the random walk, so say P is the distribution, so you start with all uniform distribution, right, and then over times you multiply P with Q, whatever Q transpose or Q doesn't matter, you multiply P with Q, this is the Q, okay, and you keep on multiplying this thing when you see the stationary distribution, meaning that after multiplying, right, you would see a certain stage, you would basically reach a certain stage where even after multiplication you get the same P, right, and that's called stationary distribution. So at the end of the day you would have a P, right, which would give you the stationary distribution, and you would have probability associated with every node, right. So the size of this vector is n, right. So if you unfold it, what you are doing? You are essentially doing this thing. You are multiplying, say this is U, okay, and these are the nodes which are pointing to U. So essentially you are multiplying, you are taking the summation of all its neighbors, prestige, right. In our case prestige is basically P, right, and what are the neighbors? How do we know which are the neighbors? You will get it from Q, okay. So for every node you are calculating this one. If you write it in a matrix form, you are basically multiplying P times P and Q, okay. So now, once we reach the stationary distribution, you are done. Okay. So so far we haven't explicitly understood the relation between W, P, Q, all these things, right. So let me now derive this thing in a different manner. I hope you understood the entire concept. Now I am defining it a different manner. Okay. So what is the idea? The idea is that I do this, I repeat this random walk with restart, right, and the expectation is that the page rank value of the positive nodes should be higher than the page rank values of the negative nodes. Okay, D set of positive nodes and L set of negative nodes. Okay. So what is our optimization function here? The optimization function is we minimize W with respect to W, right, and W is a parameter such that PL less than PD for all LD, where L belongs to L and D belongs to D. Let me explain. So we want that our random walk process would produce a rank list or a page rank value such that all the negative nodes would have lower page rank values compared to the positive nodes. Okay. And W is the parameter. So the entire thing is remember. So how do you calculate P? So we calculate P based on Q. I am actually moving backwards, right. So I will obtain P. P is dependent on Q. Q is dependent on F, and F is a function of W. So ultimately P is also dependent on W, right. So we minimize it. Why we minimize it? Because we want that we prefer shortest smaller value of W, right, smaller parameter values just for regularization. Okay, because if we make it high, then you may end up overfitting or whatever. I mean, you may explicitly extensively give more weightage to some features which are not that important. So this is the objective function, and let us denote this by FW, right. But this is actually hard. This is hard constraint, right. If you know SVM, support vector machine, right, you will understand what they mean by hard. It is hard because it is very difficult to guarantee that for every pair of L and D, this will satisfy. Okay. So the way we calculate soft margin in case of SVM, right, we do the same thing here. So we define a loss function. So this H is the loss function, okay, and what does it do? It basically says that whenever, now for every pair, okay, for every LD pair, whenever I see that PL is greater than PD, right, I will penalize. You see here, if PL is greater than PD, this would be positive, and this part will positively contribute, but we minimize it, so that's bad. Okay. If PL is less than PD, then it's okay because it's negative and we want to minimize, that's okay. Okay. So this is a loss function, and we will discuss what kind of loss function they have used in their paper. And lambda is a regularizer, okay, which basically gives a weight between this part and this part. Okay. So now how to solve it? It's a standard optimization function, although it is not convex, but you can still use gradient descent to get the values, right. You take gradient descent. I am not going into details of this mathematical part, but you take gradient descent and you essentially would be able to update the values over different times. Since this is not a convex function, what you can do, you can start from different seed nodes and you try to approximate it. Okay. So now let's look at some of the components, right? The first component was this hx, the loss function. So the loss function, in their paper, they used a simple squared lot function, which is this one. Okay, or you can do even complicated loss functions like this. Okay, or this one, right? So this h was unknown. Now these kind of h functions that you can use in the optimization, right? So the other one which was missing is this fw, right? How does this f function look like? So in their paper they used two types of functions. One is this exponent based function, right, where it is simply e to the power w times phi uv. Okay, or you can do you can take some sort of logistic function, 1 by 1 plus e to the power this one. Okay, so that's all. Now let me go back again and recap what we have discussed. So first we have this adjacency matrix. We separate out the positive samples and negative samples. Positive samples are those nodes which are connected. Negative samples are those which are not connected. Then we compute this psi function, right? Psi can be any function. It can combine, right? Then we have this f. The f is a parameterized function, right? F can be this or this. From there we get AUV. So AUV is not normalized. So from A we will get A dash or Q dash, whatever. So Q dash is the stochastic transition matrix. From Q dash we will get Q. Q is the final transition matrix which combines two factors: the stochastic part, whether you jump through one of the outgoing edges, and the second component was the random jump. Combine them, you get the actual transition matrix Q, and then you repeat the page rank, right? That's the process. So you see how you can utilize the node level attributes, edge level attributes, as well as the topological structure in a nice manner, right? The problem in supervised random walk is that it is time taking, because you have to do this random walk with restart kind of process for every nodes, and you have to take all pairs. Although you can do some sort of, you can take negative sampling and so on and so forth to squeeze the sample space, but still you need to do a lot of, you basically need to do random walk restart for every node, from every node, right? So that's time taking. Therefore it is not scalable. The crude version of it, the paper which was published in 2011-12, that paper was not scalable for a massive network, but then people actually took this thing forward, tried to make it scalable, and so on and so forth. Okay, so this brings us to the end of this chapter. So we have discussed one of the important applications of social network analysis called link prediction. We have discussed heuristic based approaches. We have discussed maximum likelihood kind of approaches, unsupervised approaches. We have discussed the supervised approach to deal with link prediction problem. We also discussed metrics, which we generally use for evaluating link prediction methods. Okay, so we stop here. In the next chapter we will discuss another important application, which is cascade, right? Cascade growth prediction, information diffusion, and so on. Thank you.